Right, in order to understand the Earth's atmosphere, I would like to introduce a history of the Earth's atmosphere that starts all the way back at the beginning, to give you a more full understanding of how our atmosphere as well relates to other possible planetary atmospheres, and also to what might happen to our atmosphere in the future. I think that it is important to see what all of the conditions were that made the Earth as we know it, with the atmosphere that it has, possible. So let's start then at the beginning. About 15 billion years ago, the universe as we know it began with a Big Bang. Now this is called the Big Bang Theory. So although I'm treating this as fact, I'm not calling it the Big Bang fact, because there was nobody there taking pictures of it. We just use the evidence that is available to us to make the best guess as to how the universe began. And it's possible that this will be updated in the future, but we have good reason to believe that something that at least looks like a Big Bang occurred 15 billion years ago. Now, what was this? Well, we can think of the Big Bang as being a rapid expansion of space and time from a singular point. So the singular point then had a high concentration of energy. And so you could imagine then, and we believe that there's something like 2 trillion galaxies just in the visible universe. You could imagine all of that, plus who knows how much more of the universe there is that we can't see. All of that. Imagine it smashed down, maybe even smaller than the head of a pin. And then for some reason which is as yet unknown, it expanded rapidly. Okay, so this is like an energy fireball as this thing expands. And so this would be the point of origin, highly concentrated energy. In a small volume. In some theories, the volume is 0, but we don't really believe that it was that small. But it may have been so small in this early stage that size wouldn't even have meaning anymore at that kind of a scale. And so for some reason then, this thing started to expand rapidly. So it's interesting that we call it the Big Bang, because it started from this point of almost infinite smallness, so it wasn't big. And there was no air to transmit a sound, so it couldn't make a sound. So it wasn't big and it didn't make a sound. But still, everybody knows what we're talking about when we say the Big Bang, and that name has stuck. And so we have this expansion then of this highly concentrated region of energy, and so it expands outward at the speed of light. Now, according to Einstein, mass and energy are equivalent and are related by this famous equation, E equals mc squared, where E is the energy. In this context, we can think of the energy as being the energy of this basically incredibly concentrated region that becomes the entire universe. Eventually it becomes everything that we know of in the whole universe. M is some equivalent amount of mass, and c in this equation is the speed of light. And so c is a big number. You square that number, you get a really big number. And so what this tells us then is that a small amount of mass is equivalent to a huge amount of energy. So in our present day universe, if we say blow up a bomb, like an atomic bomb, we're turning mass into energy. The sun turns mass into energy in order to shine brightly and create our weather patterns and also life here on the earth. And in that process, mass is being turned into energy. And so that is what's happening in the universe of today, mostly, is that mass is being turned into energy. And as that happens, that conversion of mass into energy gives us the energy we need to be alive. But in this ancient time, when the universe was very young, in the first second after the Big Bang, energy was being turned into mass. So it's thought that the first second after the Big Bang is the most important. Why? Why is the first second after the Big Bang the most important time? Well, because the most significant things happened during that time. The energy fireball converted into mass. So it's the reverse process of what we see happening in the universe today. In the universe today, we have mass being turned into energy. But in the first second after the Big Bang, it was the reverse. Energy was being converted into mass. And so an analogy to this would be, let's say, water vapor during the daytime. You might have a little bit of humidity in the air. But as the temperature drops, the water vapor starts to collect into little droplets that form on leaves when we reach the dew point. That's a weather analogy too, which is good. And so you walk outside in the evening, let's say with your socks on, and you walk over the grass, which was dry during the daytime, and because you reach the dew point, all of the little droplets get your socks wet. And so that's an example then of the temperature cooling enough so that something that was in a vapor state could turn into a liquid state. So the analogy here is that the expanding fireball, as it cooled during that first second after the Big Bang, it cooled enough so that some of the energy could condense into mass. And so that mass then, that was formed in that time, makes up all of the matter in the whole universe. All of the trillions of galaxies and hundreds of billions of stars in each galaxy and all of the planets that go around them were created in this first second following the Big Bang. So that was important. If we look up at the data projector, we see some of these points summarized. Now, when we talk about the age of the universe being 15 billion years, that's just an approximation. Some of the more recent estimates have pinned it down a little better to perhaps 13.8 billion. So that's, if that's correct, then that shows that we're getting much more precise to three significant figures. We're starting to understand what's going on with the beginning of the universe. And then it began with a rapid expansion of space and time from a point of high concentration. Most of these significant events happened during the first second. And so I'm not going to go through all of these things that happened, but here this is time being plotted on the horizontal axis. On the vertical axis, we're plotting the temperature of the expanding universe. And so we can see how high the temperatures are, 10 to the 35th power. Then down to 10 to the 30th power, that would be degrees Kelvin. And then all of the forces of nature created, the properties of the universe, the production of elements, and then this is the first second after the Big Bang. This is a logarithmic scale, so this is 1 second. Looks like a lot longer than this, but on a logarithmic scale, we're talking about massive powers of 10. And so the universe basically, since that first second, has just been winding down to where it is today, but with the properties of the universe that were determined during the first second. So if we continue on with the history of the universe, about 500,000 years after the Big Bang, the first matter formed. And that matter is, for the most part, hydrogen and helium. And so the way to understand that, hydrogen is the simplest of all elements, has 1 proton in the nucleus and 1 orbiting electron. And so after about 500,000 years, the universe cooled enough so that electrons could start orbiting around protons. So before that, it was a plasma. Which is a hot ionized gas. And ionized, in this context, means that all of the electrons were torn off. So in other words, you just have a bunch of particles flying all over the place. And so after about 500,000 years, the temperature of the whole universe cooled enough so that matter could form in its present form. So atoms started to form. Helium is the second most common element. It contains 2 protons, 2 neutrons, and 2 orbiting electrons. And so you had helium nuclei around before 500,000 years. But when we get to 500,000 years, the temperature of the universe was low enough so that the electrons could settle down into their stable orbits and create the atoms as we understand them today. So in this earlier time, before 500,000 years after the Big Bang, the whole universe had about the temperature of a star, or hotter. But it was still the temperature of a star until about 500,000 years ago. And so it was like one big bright ball. You could just imagine the whole universe. One big bright ball that was very much like a seething hot temperature that you would expect on the surface of a star like our sun. But then eventually, as it expands, it cools. And then atoms started to form after about 500,000 years. Going back to the data projector, we then fast forward to about 100 million years after the Big Bang, and stars started to form. And so stars could form from the atoms. The atoms collected together by gravity, and eventually they formed into stars. And then it took about maybe 1 billion years for the first galaxies to form. Where galaxies are huge concentrations of stars. So there was enough time then in 1 billion years for the stars to collect together into groups that we call galaxies. So that happened after about 1 billion years. What's the evidence for all of this? Well, the evidence comes from analyzing the light. From these galaxies. And we believe now that there's something like 2 trillion galaxies in the universe that we can see. And so when we look at the light that comes from these galaxies, what we find is that the light is red-shifted. Which means that it has basically a reddened appearance. And what does this mean? Well, this is indicative of the galaxies moving away from us. In other words, the universe is expanding. So then this is the evidence then for the Big Bang. There are other pieces of evidence too, but this is the strongest piece of evidence. It was discovered by Edwin Hubble back in the 1920s. As he analyzed the light that came from galaxies, he found that they were basically all moving away from us. at least all the distant ones. And what's more is the farther away you look, the faster the galaxies were moving. So if you put that all together and you run the cosmic movie backward, what it indicates is that all of these galaxies must have been in the same place. About 15 billion years ago. There's also a microwave echo from the Big Bang, which is basically the remnants of the explosion. And we can detect that in the microwave background radiation that we are able to analyze today. And so that's why this model for the universe is the one that is most favored in terms of giving us a feeling for how the universe began. So how does this relate to the Earth? Well, as time goes on, after the first galaxies form, time continues, and stars within each galaxy live out their lives. And what we are able to observe is that the big stars explode. This kind of explosion is called a supernova. And in the process of exploding, they produce heavy elements. Examples are some of the elements that are needed for life here on the Earth. Carbon, oxygen, nitrogen, and many others as well. And these elements then are necessary for life. And so in the early stages of galactic formation, there probably wasn't much life in the universe because there wasn't time for the big stars to explode and produce heavier elements. But if we fast forward now to the beginning of our solar system, about 9 billion years, after the Big Bang, or 4.6 billion years ago, at this point, there was enough heavy elements in the mix of materials within these galaxies so that life could form in new generations of stars. And not coincidentally, this is when our solar system formed. So we could ask the question then, why is the universe so big and why is it so old? And those might seem like questions that are difficult to answer. But if you understand what I've been describing to you here, we have the answer. A billion years after the Big Bang, there probably wasn't enough of these heavier elements to allow for new generations of stars to have, and planets to have life in them. But it took time to set the stage for life. While this is happening, the universe is expanding rapidly. So this explains then why the universe is so old and so big. Turns out that our solar system is about 1/3 the age of the universe. So what this means then is that a lot of things were happening in the universe before our solar system even got started. 2/3 of the time that's elapsed since the Big Bang happened before our solar system even began. But once it started, it was possible then to have life eventually evolve on a planet like the Earth within a very, very special solar system, which we'll look at in the next video.